You're welcome to taptalks.com. We are still continuing learning about organic chemistry, and we have reached a level of looking at preparation of alkanes. Alkanes can be prepared using a variety of methods, and one of them is reduction of alkenes. Reduction of alkenes can take place by simply by addition of hydrogen. Now, this hydrogen should be added in the presence of nickel catalyst. At a temperature of about 150 degrees Celsius. When we provide those conditions, then we shall be able to obtain alkanes from alkenes. Now, if we don't use this option, we can still add hydrogen, but in the presence of palladium catalyst or platinum. These two are catalysts. These are catalysts. Now, if we use these two, if we use the N of those two, then this reaction will take place at room temperature. That reaction will take place at room temperature. So whatever the case you choose, you add hydrogen to alkenes in the presence of nickel catalyst, use this temperature, or use any of these two catalysts, but then these ones take place at room temperature. Now, when we are adding, during reduction of alkenes, we need to note that for non-symmetrical alkenes, addition of hydrogen follows Markovnikov's rule. Now, this Markovnikov's rule simply helps us to be able to obtain, during mechanism, a more stable carbocation. We talked about stability of carbocations, and this rule is really helping us to obtain very, very stable carbocations during mechanism for this reaction. Now, non-symmetrical alkenes, these are alkenes which have got unequal hydrogens around the double bond. Take an example. One carbon has one hydrogen, and one has two hydrogens. Or one carbon doesn't have any hydrogen, one has one, or has two hydrogens. Such alkenes are said to be non-symmetrical. Now, for example, looking at this alkene has got two hydrogens on this carbon and two hydrogens on this carbon. So therefore, this one we call it symmetrical alkene. But when we compare it with this alkene, there is one hydrogen here and two hydrogens here. So therefore, such an alkene is non-symmetrical. It has got an equal number of hydrogen atoms around the double bond. So this rule of Markovnikov's rule works best on non-symmetrical alkenes to simply be able to help us on where the hydrogen must be added in order to obtain the most stable carbocation. So Markovnikov's rule says that during addition of these reduction of alkenes from alkanes, the first hydrogen is added to a carbon with more hydrogen atoms. For example, if this is carbon 1 and this is carbon 2, the first hydrogen should go to this carbon because it has got more hydrogen atoms. That's what Markovnikov's rule says. And that is only intended to help us obtain the most stable intermediate product, which we call the most stable carbocation. That is addition of hydrogen to non-symmetrical alkenes. Now let us go ahead and look at mechanism for this reaction. Now, I want us to consider a case whereby we have this type of a non-symmetrical alkene. I'm only considering non-symmetrical alkene because it has something to think about in relation to Markovnikov's rule. The one of a symmetrical alkene is just an obvious case. So we are looking at a reaction of hydrogen in the presence of nickel catalyst at 150 degrees Celsius. Now, this hydrogen is diatomic. 1 mole of hydrogen is diatomic. So we can look at CH CH3 with a double bond, then plus this hydrogen molecule which is here. And I want to say that this is 1 mole of hydrogen molecule, which has got two atoms. Now we attach the partial positive and partial negative charges to simply be able to attract the electron pairs from electron-rich species. This alkene has got 2 bonds, and each one of them carrying 2 electrons. So that means around these double bonds we are having a total number of 4 electrons. But we should not forget still that alkenes are formed by sp2 hybridization. That leads to the formation of the pi bond along here. So we are having a pi bond and a sigma bond. The pi bond is quite weak enough and can easily be broken and donated to an electron deficient species. So because we are showing that this is an electron deficient species, it is bound to receive electrons from the pi bond. And the most important thing, we should start from the bond and reach the hydrogen. So electrons should reach where they are going. We don't want a system of hanging bonds. Like for example, somebody would do this. It is not picking any, there's no electrons around there. Or the electrons are not reached where they are supposed to be going. So such a case would be a wrong one. Now, remember hydrogen takes a maximum of only 1 bond. Once it has formed a bond with the other carbon, or the other carbon, then this one should break in order this hydrogen for it to remain stable. So therefore, this hydrogen goes ahead and takes away those bonding electrons. And when it takes them, then it becomes a nucleophile, because once it takes the bonding electrons, then it becomes entirely negatively charged. Now this bond has broken. This hydrogen, there was 2, but there are now 3. And now we have a hydrogen here, which was formerly there. Now then plus this hydride. Now, a hydrogen, if it is positively charged, that hydrogen ion, we call it a proton. But if it is negatively charged, we don't call it a proton, but we'd rather call it a hydride. Now, a proton is electron deficient species, while a hydride is electron rich species. This is an electrophile, while this is a nucleophile. So therefore, it can go ahead and donate electrons. But because when you look at this carbon, is having 1, 2, 3 bonds, then should acquire a positive charge. So then finally, during terminating of that mechanism, we would have CH3, CH2, CH, then this carbon is carrying a positive charge. Then this hydride, since it is now a nucleophile, will donate its lone pairs of electrons to finally form CH3, CH2, CH3. This is now an alkane, and we call it definitely propane. Definitely call it propane, yet this was called propene.